So I'll just going little fast because it will be short on time. So locality is basically, as already mentioned, the neighborhood of that particular node. So if you say one hop neighborhood, then only the neighbor would be considered. But if you consider two hop neighbor, then neighbor's neighbor would also be considered. For example, in this case, this and its neighbor, this, and this. So these are basically uh, locality that is there. And this can be considered similar to the kernel of the CNNs. So aggregation side. So aggregation is just summing up of the node features. So I'll just show the example after this, where we basically consider the features of this A and C to embed in the feature of B, and that eventually gets the output for the A. So this is basically summing up, or you can say aggregating the features of uh, neighbor nodes and its neighbor nodes to the target node that is there. So for example, for A target node, if we consider, so A's immediate neighbor is D, C, and B. So these are the immediate neighbor. But now B is connected to C and A both. So we need to consider for B, we need to consider A and C here. Same thing for C and D. So these are neighbor's neighbor. In such a way, we are able to get the feature of very far away node as well to the target node. And that able to generalize, or you can say that generalize the embedding of that model very well. And these are the basically computation graph. I will just show an
Aditya, I think we have lost you.
hello.
Yeah, I think we lost you for a couple of minutes.
Okay, okay, yeah. Sorry, there is a power
That's
outage
okay.
currently.
Oh,
So is the presentation visible?
no. I can see your camera, but not
Okay, I'll
your
just
screen.
share it again then.
Sure.
Okay, now is the presentation available?
Yes.
Okay, yeah. Okay, so we were at the aggregation stage. So what these black boxes in this aggregation state are there? Means what actually they are. So in general, they are just the neural networks at this locations, basically small neural networks. And the zeroth layer embedding is nothing but just the feature vector of those particular node. For example, this has some feature x1, x2. So maybe in the next slide, you will get an idea. So for the zeroth layer, it is just this feature vector, but in the consecutive layer, it is an embedding of this neighboring nodes as well. And how this is getting aggregated will get a better idea in the next slide, basically. And composition is just, as already mentioned, the first layer is just the initial layer, and that is the feature vector itself. So this is basically the layer number, and this is the node Q or V, whichever it is. This is the feature vector. Now this is the parameter. So this is basically average neighborhood. So consider we are having neighborhood of 2. Then we will take the 2 hop neighbors of this node V, and we will get the normalized embedding for those particular neighboring nodes. and this is the previous layer's node V value. So on equation side, you might not get a clear picture, but the slide after this, where I have got a graph there, you will get a clear understanding what this basically equation stands for. So this is previous layers embedding V, and these are the trainable weights, or you can say parameters, basis vector and the weight vector of the layer. And this is the sigma is the non-linear activation function. This can be ReLU, sigmoid, 10H, etc. And this is the output embedding for that particular layer. The layers can be multiple, 1, 2, 3, whatever it is. And that is the embedding of that particular node in the embedding space. So yeah, so this is again optimization problem. So stochastic gradient descent or any optimization, Adam optimization can be used to calculate this loss function and minimize the loss. So what happens in message passing layer? So this is the actual thing that you can understand by graph. So this is our graph and green is our target node, you can say. So we are currently calculating for the green node. And these are the features, individual node feature vector of all the nodes. This is blue, yellow. So x1, x2, x3 can be anything. So consider an example of a male and female graph, or you can say social network graph. Then there would be the features like height, weight of a person, uh, its relationship with the other person, something like that. So those all are in the feature vectors here, this thing. And now we are calculating the embedding for this uh, target node, green one. And so what happens actually in message passing layer? So we pass a message, or you can say a signal from its neighboring nodes to the target node. So for this target node, we have got three neighboring nodes, 2, 3, and 4. So we pass the signal, or you can say for the zeroth layer, it's just this feature vector to this node. So we'll calculate for the first layer, consider it, right? So for first layer, there would be 2, 3, and 4. So we are passing this as the message, or you can say this feature vector, this three feature vector as the message. Now, this is just a terminology that the graph neural network follows, but consider these as a signals, right? So for this kth layer, these are the signals that we have. Now we aggregate this thing, three layers, because those are the direct neighbors of the target node. So when we aggregate this thing, what we get is something like this. Now this is the first layer output embedding for this target node. So as you can see, we have got something yellow color here, right? So we have got some information of this neighboring node to this target node in first cut itself. But we don't have the information of this blue node currently. It is neighbor's neighbor, it is neighbor of the fourth node. So once this is the output, we'll update this embedding in the graph. So what happens is now we get this embedding. So this replaces the input vector. Same thing for the other nodes takes place in the background, and all these nodes, all this embedding gets updated. The feature vector get updated, and they get some information about their immediate neighbors in the first passing itself. So for example, for this fourth node, it is a neighbor. It has got neighbor one, that is the green color, and 5 is the blue color. So if you see in the embedding layer, you have got this blue for the 5 and green for the 1. So you have got some partial information from your neighbors already in the first pass itself. When we pass it for the second time, there are chances that the information about this blue node is passed to this green node itself. So this green node will be aware of some features or some structure of the blue nodes also. So if you update it, will again pass the message. Now this is the second time, second passing layer. One layer we have already passed. Now we are passing to the second layer. For second layer, what we have got the output as the from the first, we'll use it as itself. Now it's the same thing. We'll take this target node's feature. We'll take its neighbor's feature. Now we'll aggregate this, the neighbor's feature vector. And what we'll get is the output of the first layer. So if you see this, now there is something blue color here. So color is just for your reference. There might be some feature that might be affecting or that might be affecting the structure of the graph. Layer node, it's also color is high. So this node now, when you, so the first one has also got information about something blue. Also for the green. Green is itself and yellow is its neighbor. So we have aggregated this information say target node. So now the target node has got information about all the nodes that are present in this graph. And this is basically the structural information or embedding that is used for prediction level tasks. Now this can be local feature. So based on this local feature, we can predict that if the phi is a smoker or a non-smoker, for example, based on this feature vector that we have got. And if you say on a graph level base, then based on a graph structure, if this molecule is a medicinal molecule or is a harmful molecule, that can also be predicted based on the aggregation of all the nodes feature. So this is what actually message passing layer is, and we predict the graph here. So in general, behind all those mathematical equations, this is what is happening in graph neural network in the backend. And in generalized form, if you see, so for computation graph, so what is computation graph initially? So if you consider this particular graph itself, one has the neighbor 2, 3, and 4, right? So it has got direct connection with 2, 3, and 4 here. But this 4 has also got connection with 1 and 5. So again, there would be here 1 and 5. So if you see here, so this is again one, green one are 1. So for the first layer, we basically aggregate and update. So first we aggregate this thing, update this value. For this, when we go for calculating values for 2, we use this updated value of 1 and this blue value, and then we aggregate those feature vectors to 2. So this is the computation graph behind the graph neural network, where the aggregation and updation takes place step by step. And this is true for all the graph neural network algorithm. It is just the function that aggregates and updates, those are different. So these are the number of message passing layers. These are hyperparameter basically, means how many message passing layers do you want. For example, currently we have 2 times. As I explained in the previous example, we have got 2 message passing layers. You can have again one more 3 message passing layers. So with multiple number of message passing layers, the depth of information from the graph gets aggregated to the target nodes. So the graph is, if the graph is deep, very deep, then you might want to increase the number of message passing layers so that it can get information about those far away nodes as well. So this is the main glimpse of what message passing layer is and the graph neural network. So as in this example, this was the target node, this one. We aggregate this yellow nodes. So this is just a comparison with the equation that is there. And once that is aggregated, we get the output node. So these are the terminologies that are defined by GNNs, and just the function to calculate this aggregate and to update this is different for different graph neural networks. For example, in spectral nets, those are different in the GCNs, those are different. So those functions are just different. Rest everything remains the same behind it. So now we'll go to geometric deep learning layers, or you can say various architectures that are there. So for convolution, we'll go for convolution and pooling, and those also in just brief detail. So convolution are of two types, spectral and spatial. So the spectral convolution is based on the frequency domain, where we use Fourier analysis to get there, and we basically use eigen decomposition. That is the main thing in spectral convolution. In spatial convolution, we don't use eigen decomposition. We directly use message passing as itself, and it is simple compared to spectral one to understand. So in spectral convolution, as I already mentioned, we use concepts for signals, or you can say Fourier transform, to represent the features basically. Represent the nodes, we use signals, while here we use message passing as already mentioned in this previous example, what actually message passing is. So subnets, or you can say this was initially means introduced spectral convolution. So this is its equation, so I'll not go into detail. So it basically uses Chebyshev polynomials here for convolution. So it is similar to Taylor series approximation. Chebyshev polynomials are something like that. For example, first level are 1, 2x square or something like that. 4x cube minus 3, something like that. So you can find out the polynomials on Google easily. And okay, yeah. So those are being used or multiplied with this scale Laplacian. So this is the scale Laplacian matrix that is there, and that is the diagonal matrix. This is the sparse one. It depends upon the size of the graph, the size of this matrix, and that is multiplied with the Chebyshev coefficients, or you can say polynomials, and aggregated for the number of uh, order of the node, or you can say order of the polynomial that is used. For example, second order, third order, fourth order. So there is no limit for Chebyshev nets on the order of the polynomial. You can go up to n order polynomials. And what does that order means actually? So in visual representation way, it is like to what neighbors you want to aggregate the information with. For example, if only one order is there, then it is just the neighbor, immediate neighbor. But the second is there, then you want to consider features of neighbor's neighbor. So as we go on increasing the order of the polynomial, we try and go into the deep depth of the graph to aggregate the feature information. So as I already mentioned, it has no limit on the order. Basically, you can go up to any limit. So GCN, so this will go in the lab session as well, GCN. And this is a simplified form of Chebyshev net, you can say. And there are some optimization or simplification done so that the eigen decomposition that is there, which is performance intensive, is ignored while doing graph convolution network. So here also, these are the same, the parameters, or you can say Chebyshev polynomials are only used but the level of or the order of the Chebyshev polynomial is fixed. You cannot go up to k polynomials here. So it is just two, I guess. Uh, yeah. So with that, this GCN is further simplified. If you see the paper of GCN, you will be able to understand how this simplification is done. But I will not explain that. I will just directly, yeah. So we have limit the value of order of the polynomial to one only. So I'll just give the simplified equation for the GCN, and this actually we will implement in the lab session for calculating the convolution layer. So this is the constant term actually that they have smartly classified, or you can say simplified in the paper. And this is the adjacency matrix, and this is the degree matrix that we have already discussed. This is the feature vector, and the theta is the parameter value. So with this, we'll get a convolved matrix representation of the graph. Yeah. So how we come up to this simplification is well mentioned in the paper. So if you read the paper for graph convolution network, you will get an idea about that. Now moving on to spatial convolution. So graph sage is one of the mostly used uh, algorithm or architecture, you can say. So here we take a fixed size depth of the neighbors, and we aggregate the information of only that feature. So this is not something will increase on different nodes. So for example, for this red node, blue and green features would be aggregated if the parameter, or you can say uh, k is equal to 2, so second order basically, and we aggregate those information. And this function, the aggregation function, can be addition, averaging, or anything that can be different thing. And this is the neighbor of V. So this neighbor is basically, if you consider k is equal to 2, then we'll go to neighbor's neighbor as well. So all those comes into neighbor of V, and we'll calculate the signals for those. Yeah, so as mentioned, aggregation function can be mean, sum, or max. So uh, so if you consider compared to the generalized GNN thing, then this is the aggregate function, and we update the value to get this particular thing. So the aggregation function here is different. For graph convolution, if you go, then the aggregation function is different. We use Chebyshev polynomial here. And same thing for Chebyshev net, the aggregation function is different. So if you think in a high level view, the equation that I previously mentioned, where we have update and aggregate function, that is a generalized form of graph neural network. And what actually the aggregate function will do, so that is dependent on this particular implementation for individual architectures. So for GCN, it is this particular thing. Don't consider X, it is theta and this constant. So for this graph sage, it is aggregation of its neighbors. Basically, this is the aggregate function. Now, if you go to graph attention network, so in lab, you have already implemented this, so you have to just run it. So what it does, it is just, if you visually or conceptually understand it, we are giving certain weightage to certain nodes additionally. So we want attention of such some nodes, some particular nodes, and that is being calculated using this additional attention parameter, alpha ij. And this is nothing but this is softmax function in general, where we have again used non-linearity of Leakey-Rayleigh function. So in whole, this is just a softmax function, and this a raised to t is the learnable parameter. So here there would be a single layer, you can say linear projection layer, which will calculate, which will have weights of 80. and that weight we will use for calculating the attention coefficient. And this attention coefficient is basically determining which node features we need to concentrate more on. So this is in general overview of what graph attention network it is. As mentioned already, this is just a softmax. So this is to normalize the value of the soft probability. We basically divide by all the neighborhood sum basically. So once we get this attention coefficient, we multiply, additional multiplication is there along with the weights, and this is the signal of the jth node, you can say, to calculate this signal of the ith node. And this can be again activation function, which can be ReLU, sigmoid, or anything like that. Now, when we go to pooling side, so I haven't gone anything in detail of the pooling side, different types of architectures, but in general, what is pooling? So in convolution neural network also, we saw that there was one huge image, but when we pooled it, consider it 5 by 5 or 4 by 4, something like that. And when we pooled it with a 2 by 2 kernel, we just got a 4 by 4 matrix, or you can say you have scaled down the feature vector. So same thing it is there with pooling as well. We basically make the graph that is in detail a very coarse CNN. So these are some example architecture of pooling layer. We haven't got in detail of that because that would be too intensive for this such a short session. So yeah, as we already saw pooling, mean pooling, global pooling, max pooling, same thing it is there here as well. So we basically, you can say, uh, shrink this particular three nodes into single node based on their structural equivalence. And we get a smaller structural equivalent graph there. So this is the pooling layer in a graph convolution network. So we'll go to the application side. So some applications include certain features of the other group of people, or you can say you want to predict someone is a smoker or not smoker based on the features of the people. Is the uh, similar to image classification, like it's a cat or a dog. Similar thing we can do on graphs. The medicine is sorry, the molecule is a medicinal molecule or a harmful molecule, something like that. Link prediction. So as I already mentioned, recommender system in your e-commerce website. If you buy one product, you get recommendation based on the product you have bought. For example, if you buy a mobile phone, there would be a recommendation of the mobile cover that you have bought, charger, or the earphone for that particular product. So for that type of application, link prediction type of uh, we can use graph neural networks for link prediction in that case. So GNNs are currently used in natural language processing extensively nowadays, even for text classification, because as you can consider the text, or you can say the sequence data can also be represented as a graph. For example, in a sentence, there are multiple words, but those words are in certain sequence or certain graph format, you can consider it. And that is the reason why this is nowadays more popularly used in language processing applications. In chemistry, so as I was mentioning about molecules like harmful molecule or medicinal molecules, or to identify the compound or protein structure basically. So for this COVID virus also, there is some certain sequence of protein in the structure of virus, and that data can be used to identify if this is a COVID virus or it's a mutation of a COVID virus, or you can say by altering some node, or you can say some protein, uh, can we get its antiviral or not? So such type of application can be done, but for that you require a lot amount of data, and so this is basically an application of GNNs in chemistry or pharmaceutical side of thing. Now coming to a geometry thing, then l- learning shapes information from point cloud data, mesh, surfaces, VREP, etc. So in that situation, we can use this graph neural network to predict a classification or segmentation based application, you can say tasks. So there are nowadays a lot of research paper in this particular field where PointNet is one of the thing. PointNet plus plus, it is based on this PointNet architecture. Mesh CNN is there for which works on mesh data directly. So, but these are just currently used for academic purpose only. For actual industrial applications, still lot of research is required, and now industries are coming up with more such type of application built into the application. So currently, this is the hot topic for all the industries in CAD/CAM dealing with shapes and modeling kernels to introduce this machine learning in general in the field of CAD/CAM. And I'm also interested more in such stuff. So I will go ahead in the next slide with some of the application in Dassault systems. This is not in particular GNNs. It is overview, or you can say overall artificial intelligence or machine learning that is been used in Dassault system. And it is not GNNs behind. Let me clear that one thing. So yeah, Aditya, you can just switch off recording.